Hello, my name is Daniel Grimmer. I am a postdoc here at Yale in the philosophy department. This is a talk I gave yesterday at the Elm City talk series, and I'm going to re-record it now and post it on YouTube. So the subject is evolutionary epistemology in silico, basically what we can learn from neural networks about nature and nurture. So nature and nurture is a very long debate in philosophy. On the nativist side, who believe in innate structures, we have Plato, Descartes, Jung, Chomsky, Kant, these kinds of thinkers. They are all united in thinking that the mind possesses a lot of preloaded domain-specific structures which are prior to or in support of experience in some way. Jung's archetypes, space and time, and the categories from Kant, Chomsky's universal grammar, etc. There's a very rich tradition over here. Opposed to this is the empiricist camp, the likes of Aristotle, Locke, Hume, Skinner, and many more, who think we start off more tabula rasa, the blank slate, no innate structures really, or as little as we can get away with, and then we learn massive amounts from sensory data in a very general purpose way. Humean associationism, identifying patterns and statistics from the environment, and this is supposed to be the method of cognition, basically. Now, these long-standing debates in philosophy connect in interesting ways with modern AI techniques. So the current successful AI techniques, what's most fruitful recently has been neural networks and the kind of scale mentality, where we just throw a ton of data at the system and don't try and do any significant hand coding or writing in of our human expertise. This is Sutton's bitter lesson, and it's proved very, very true in recent years. Although who knows if it stays true. But on the other side, we have the good old-fashioned AI approach, which was popular in the 1950s to the 1980s. This was a lot of hand-coded logic and rules for symbol manipulation being written directly into the AI. So lots of human expertise went into these things, and very logic-driven, very much symbolic manipulation. So these were the kinds of AI where if you tell them a paradox, then their sort of head explodes, and this is the way to stop the evil robot. Now, the program that I am on is to take these empiricist methods here in the bottom right corner and carry them over into the nativist side. So I think you can take the empiricist methods, what's currently working for them, and really they're not attached to the empiricist program at all. You can take them and move them over to the nativist side and then use them to say interesting things about these innate structures, both scientifically, how are they realized in neurons? What's their evolutionary history? But also interesting philosophical things about them, which is what my intention here is. That's the program in one slide. But how can we do this? And more importantly, why are the neural networks so much aligned with the empiricist program at the moment? It is a matter of engineering fiat that I say, I'm claiming here. So let me review first how they're typically trained, and then we'll get into a different way of training them, which aligns them with the nativist program. So how does a neural network typically learn? In a single training run. So think one lifetime, if we're going to make some evolutionary connections later in the talk. They start off essentially tabula rasa. So they have random initial parameters. That's what I'm calling theta zero. And now that's a vector in a very high dimensional space, millions of parameters in there. So think of it as many, many numbers. In some kind of fixed architecture, yes, and arguably there is some innate structure or encoded in that architecture, but we can set that aside for now. It further aligns with the empiricist program because it's a very general purpose kind of learning which goes on. So the performance of the network is quantified in some way by some objective function, L of theta. And then the weights and biases, all these tunable parameters in the model, are changed from theta n to theta n plus 1. There's an update rule, and that's some learning algorithm A, which is meant to apply in a very general purpose way. For instance, here is gradient ascent. So you take the loss function, compute it where you currently are, and take the gradient, which points in the direction to maximally increase it. And then if you want to increase performance, you just take a step in that direction. Right? And these systems are known to be universal approximation machines, or at least they have that representational capacity so that they can learn in principle any pattern given enough data. Now, how much data does it take though? It's an evolutionary amount of data ultimately. If you look at ChatGPT 3's training scale, it was something like 300 billion tokens. And as a matter to compare this with our own timescales, think of 100,000 years of behavioral modernity and 20,000 words a day in terms of how much language we hear. That's 730 billion words, which comes to something like 1 trillion tokens. So this is comparable. And the current training runs for these models are regularly in the trillions of tokens. So it's a kind of evolutionary scale of data which has to be pushed through these models in order to get them to competence. Now, obviously, humans are not taking an evolutionary scale of data to learn language. We learn language much quicker. There's something called the Baby LM Challenge, which is trying to get the language acquisition speed of LLMs up to a kind of human scale. And they set the mark at something like 10 million to 100 million tokens, which is much less than the 300 billion or 1 trillion, which is currently being used. This connects in a very important way to Chomsky's poverty of stimulus argument, which I will now paraphrase. So the linguistic data that a child receives is so sparse and the grammatical structure of human language is so subtle that the language acquisition is only going to be possible if we're really given a huge head start in the form of something like a language acquisition device. Or Chomsky spells this out in terms of innate knowledge of a universal grammar. Right? It's also called our innate language faculty. I use these terms more or less interchangeably, although there are, of course, differences between them, but that's not important for this talk. Continuing with Chomsky's point of view, language acquisition for him and his program is not a general purpose pattern matching. It's just our innate language faculty growing along a kind of developmental pathway that was carved out by evolution. Here's a quote. Language development really ought to be called language growth because the language organ, a kind of mental organ, grows like any other body organ. So he takes this kind of developmental analogy very seriously, and I'm going to come to lean on that quite a lot in later portions of the talk. Or not lean on it, but give it a lot of support, in fact. Now, what does Chomsky then make of these large language models? Here is a reconstruction of his argument from The False Promise of GPT paper. As we already noted, LLMs access massively more linguistic data than a child does. Again, this 300 billion, or now in the trillions, versus 100 million for a child. Relatedly, the large language model's tabula rasa approach, which I highlighted earlier, is completely at odds with our innate language faculty, which Chomsky claims we have, and it's forced onto us by a kind of poverty of stimulus argument. Now, relatedly, again, the LLM's general purpose learning method makes it a giant pattern matching machine. It really just is a stochastic parrot, Chomsky would claim. So eventually it could produce any statistical pattern and it could learn, for instance, impossible languages. I should say a little bit about what these are. An impossible language, for instance, would be one that disrespects the hierarchical structure, which is common to all languages. So languages are structured in clauses and clauses within clauses, and there's a hierarchical structure. If you diagram a sentence, it makes a tree, you know? So the linear word order is not a function grammatically. You can't say take the second word and the seventh word and make them trade places as the mark of forming a question, right? That linear word order is just not part of the grammatical structure. So it'd be very, very artificial to do that. Now, our language acquisition device, again, a kind of Chomskyan argument, is a very domain specific. If you try and teach an impossible language in these studies to an adult, it's treated by the brain as a kind of logic puzzle and processed in the frontal cortex, not in the Broca's area in the language center, right? So this says that the mind receives this thing and says, oh, it looks a bit like a language, but I'm not going to send it to the language center, which has specific linguistic characteristics. And that's, of course, where our language acquisition device lives and operates. So these kinds of impossible languages wouldn't even get routed to the language center to be learned by the special language acquisition device that we have. Again, this is a kind of nativist linguist view, which you don't have to buy into. I'm just rehearsing Chomsky's arguments here. So from all of these points, Chomsky comes to a conclusion that large language models are really terrible models of language use and acquisition. Basically, linguists should set them aside, ignore the hype, and keep doing linguistics in the way that we're used to. These systems can't teach us anything about human language use or acquisition because they sit so firmly on the empiricist side whereas Chomsky's nativist linguistics is totally of a different kind, right? So Chomsky has this wonderful critique, and very sharp, against LLMs, but I should say it's as they are typically trained. Of course, as I said, my whole program is to take these empiricist methods and put them to good use on the nativist side. So I have to see that there's some way of getting around these arguments, and we're going to end up with a suggestion that we can train an LLM to completely satisfy Chomsky's requirements by training it in a very different way than the standard empiricist way. So the question is, can we modify and redeploy the AI engineer's fancy new tools in order to construct really a scientifically useful model of human cognition? And I have a particular focus on its evolutionary history. So let me tell you what the bold claims are that I'm going to make in the talk. Is yes, there are alternative ways to train neural networks which efficiently and faithfully simulate the kinds of cognitive evolution which shaped human cognition. So we can do evolutionary studies properly evolving innate structures using a special meta-learning technique, which I'll describe in the next portion of the talk. I think, and I have a good proof of concept, that if you were to apply these to a large language model, it would naturally evolve something which is functionally equivalent to a language acquisition device in a very thorough kind of Chomskyan way. Now, you can also evolve a spatial intuition into a transformer, connecting with the Othello GPT paper. We'll do this at the end, but this is another kind of innate structure which you can sort of access through these kinds of evolutionary techniques. And at the end, I'll talk about cases in which different species might evolve different kinds of spatial intuitions, not just that bats have a different umwelt than us, but that like real aliens might have a completely different spatial categorization of the world. But again, the purpose is to take these nativist or take these empiricist tools and bring them into the nativist program to do some interesting scientific and philosophical work. So to highlight where we're going to go, in the next portion of the talk, which will be part 2 in the YouTube series, I'll talk about evolutionary meta-learning, which is an evolutionary interpretation, a new one that I've produced in a recent paper that I'll send out a link to, of existing machine learning techniques which are called meta-learning. They really are, if you look at them correctly, a proper evolutionary simulation. Then we'll apply this to large language models, and I'll suggest that we can evolve something like a universal grammar, or an innate language faculty, or a language acquisition device, pick your terminology. We can get one of those inside of a large language model. Then I'll turn to our spatial faculty and suggest that we can evolve one of those again. Okay. That's it for this portion. I'll see you in the next talk.